Okay, so I want to look at one application or one more application of the cross product, and it's how do you find an area of a triangle or even a parallelogram given its coordinates, given its 3D coordinates. Okay, and for those of you who have a really good memory from honors geometry, we learned something called the Shoelace Formula, and actually that's basically what we're doing. Shoelace Formula actually was finding the area of a triangle given, well, you were given coordinates in 2 dimensions, but the 3rd dimension just would have been the same coordinate, and so therefore everything would have canceled out. It would have been in the same plane, or like the flat plane of the layer Z would have been 0. Okay, but so here's what we're going to do. So we're going to take a look, this is so crazy, like application, and again, we wish we were in class, we could see this, demonstrate it, prove it. For those of you who will go on to linear algebra, you'll get a chance to see this as well. But let's say you've got these like 3 points in some, as long as they're non-collinear, they'll form a plane. That's one of our theorems. So some 3 points in space, like here, let's say here and here, and you want to find the area that connects those 3 points. That's enclosed. So like if I could find this, and if I could find this, and I could find that distance. So one way I could do that is actually use Hero's formula, find the length of each side, not too bad, but it's not going to be clean in terms of, in terms of square roots within square roots. Okay, so here's what we're going to do. What we're going to do is we're going to actually think about, well, let's come up with the equation of the plane that contains these 3 points. And in order to do that, we would need the normal vector. And so to find a normal vector, what we would need to do is define a position vector from one point to another. And again, you could pick any of the two. So maybe I'll do that one to that one, and then I'll do this to this. So let's find those position vectors first. So let's say if I'm going to go from this point to this point, again, order doesn't matter, so I could have gone the other way. 2 down to -3 is -5i. 1 down to 0 is -j. 0 up to 4 is +4k. And then let's say I wanted to go from this point to this point. So 2 down 0 is -2i. 1 up to 2 is +j. And then 0 up to 2 is +2k. So those are 2 vectors that are position vectors, and I could have picked any of them. And then next we're going to do is we're going to find the normal vector, the vector that's perpendicular to both, the vector that's going to sort of come off the page, because that normal vector, whatever that normal vector is, the coefficients that are in front of the I, J, and K will be the coefficients that take place of the plane. Okay, now, I know it doesn't say anywhere in this, like this problem, find the equation of the plane, but this is one of the applications of a cross product, is if you know those 3 points and you know the plane, you can actually find the triangle's area, which is pretty cool. So let's actually find this blue normal vector. I would just like to remove the I, J's, and K's and just like to look at the coefficients. So -5, -1, 4, -2, 1, and 2. And so then we will, block out. I'll take a nice dark highlight color here. So we'll block out the first column, and then we'll go ahead and do, pen, where's it at? There we go. We'll do our cross product. So -1 times 2 is -2 minus 4. So we get -6i. And then let's slide this over. And then remember, it's going to be whatever the opposite value was. So let me put that there. And then I believe it's a 2. Yeah. So -5 times 2 is -10 minus a -8. So -10 minus -8 is actually -10 plus 8, which is -2. There was already a negative there. So it becomes +2j. And then we'll slide over for the k. So -5 times 1 is -5, minus 2, -5 minus 2 is -7. Okay, so now we have our cross product. And remember, a great way to check is just to make sure that's perpendicular. In other words, the dot product would be 0. So if I look at the dot product between the two vectors, let's see, -5 times -6 is 30. That's a 2, so that's 28. Minus 28 is 0. Excellent. And this is 18. And that is plus 2 is 20. Sorry. How about negative 2 times negative 6 is 12. Plus 2 is 14. Minus 14 is 0. Okay. So I'm very confident that that is our normal vector. And if I wanted to find the equation of the plane, remember, I would just take those same coefficients. And just as a good review, I would take those same coefficients, negative 6, and make it an x, plus 2, make it a y, minus 7, make it a z, plus d equals 0. And then, again, we'd have to pick any one of these 3 points to put in there. Okay, what I'm going to do, though, is focus on that normal vector. And the normal vector's magnitude, which is what we haven't done yet for a while. Remember, a magnitude of a vector is its length. So if that's my normal vector, which is negative 6i plus 2j minus 7k, if I find the magnitude of that normal vector, remember magnitude is like that double absolute value sign, so it's the square root of negative 6 squared is 36, plus 2 squared is 4, plus 7 squared, which is 49, so it's the square root of 89. So that's the magnitude of this particular normal vector. It's its length. Now here's that fun application. That quantity, right? This quantity is actually that vector's projection of these two vectors in terms of if you would have done this and done this, like to figure, okay, this vector goes out here, this vector goes out here, so it kind of creates a parallelogram or spans an area, or that's this normal vector's projection in this plane. They have the same quantity, even though they represent two different things. So the area of this particular green region is equal to the square root of 89. So, which is weird because it's the same thing as the length of that normal vector. So like this is a linear measurement. I might say that's root 89, let's say like centimeters if we're in centimeters, but the area of this green region is root 89 centimeters squared, which is crazy. And again, I wish we could prove that, when we were in class. But again, still not what we're asking. We were asking for the area of the triangle, but honestly, the triangle is just half of that parallelogram. So then you just take that and divide by 2. And again, if you really remember Shoelace formula, there was a step where you divided by 2. Okay, so the application that you make sure you know for this in terms of homework is that you can find the area of the triangle by finding the magnitude of the normal vector. So let's say magnitude of your normal vector, and then you divide it by 2. That'll give you the area of a triangle. Okay, so there's, I think, one practice problem to do on a Canvas quiz, and then if you have any questions, certainly please send me an email, and just keep working on the homework, and thanks again for watching this.